Ceramic fillings and ceramic joint and bone replacements are highly used today in the medical industry. These ceramics are hardy, resilient, strong, and lightweight, and are even compatible with blood and oxygen flow. The ceramics of the modern day are made of a compound named zirconia. This compound is instrumental in many materials for the properties it has. Zirconia has three distinctive structures, with the one best being used for ceramics being a tetragonal structure. This structure doesn't compress or shatter under stress, unlike its other forms, and has an extremely high melting point, making it ideal for all uses. This is used as the framework for all modern biological ceramic implants. Zirconia was first created in the 18th century, but people had no idea what to do with it, so it was used very little or just for minor things, like hardening glass or glossing over bricks. Then in 1972, Garvey and Nicholson discovered a process to keep zirconia in its tetragonal form. After that, it started being implemented into high-end glassware and ceramics, and by the early 2000s, people were testing out how it would be in dental implants. This turned out to be extremely crack resistant, much better than the aluminum oxide that was previously used. This is all due to the amazing metal that is primary component of zirconia, zirconium.
Zirconium was first discovered by Martin Heinrich Klaproth, a German chemist, in 1789 while analyzing the mineral jargon. Jöns Jacob Berzelius, a Swedish chemist, was able to isolate zirconium in 1824 and prepare zirconium in a pure form in 1914. Currently, most zirconium is extracted from minerals, such as zircon and bdelliolite. The process that is used to extract zirconium from these minerals is called the Kroll process.
Since zirconium is highly resistant to corrosion, its alloys are used in pipes, fittings, and heat exchangers. It is also used in ceramics and bricks. Zirconium oxide is used to make extremely strong ceramics, which can then be used in applications like teeth and hip replacements. Since zirconium does not absorb neutrons, it is extensively used in nuclear power stations. Zirconium metal has a thin oxide layer, making it resistant to corrosion. Because of this, it is frequently used in pipes and in the chemical industry. Another form of zirconia, cubic zirconia, resembles diamonds when cut and is used in jewelry. Over 90% of zirconium metal production is used in the construction of nuclear reactors. Additionally, cubic zirconia is the most economically important competitor for diamonds, due to its durability. Zirconium also has an important commercial role in construction, as the material can be used for bricks and ceramics. One interesting property of zirconium is that it is extremely resistant to corrosion and does not dissolve in acids or alkalis. Also, when finely divided, zirconium can spontaneously ignite in air, especially at high temperatures. Excitingly, zirconia has been speculated to electrolyze to produce oxygen from the carbon dioxide in the atmosphere of Mars.
The element zirconium is a grayish-white hard lustrous metal. Specific gravity is 6.4. Melting point is 3,362 Fahrenheit. It's insoluble in water with low toxicity. Production of ductile pure zirconium is made by two-stage sodium reduction of zirconium tetrachloride. Zirconium and hafnium are actually chemically very similar, and separation is unnecessary, but for use in nuclear reactions, due to the fact that hafnium derivative is slightly more soluble in methyl isobutyl cantal than in water, the method used mainly in the US is by liquid-liquid extraction of the ferrocyanate oxide derivatives. For the synthesis of zirconia alloy, producers mainly use scalp melting methods with a temperature over 3,000 degrees.